How's it going, everybody? I want to thank you guys for stopping by and hanging out with me in this video. If you could go ahead and do me a huge favor, and please like, share, and subscribe on the video, be much appreciated. Thanks, guys. How's it going, everybody? In this video, I wanted to have kind of I've always wanted to start a podcast, but I'm really not in any groups that I could be like, hey, Tom, do you want to be on my podcast? You know, maybe whatever we might call it. But I think it'd be kind of cool to have a podcast and to just talk about networking in general, and not really be so lesson oriented, meaning where I wouldn't really try to explain a technical topic, for example, but more or less talk about networking and IT related stuff and try to help those that maybe are trying to get into IT or are already in IT and trying to get from help desk to the server team, or from help desk to maybe level 1 to level 2 support, or maybe they're on level 2 support and maybe they're trying to get to the network team or the server team, stuff like that, and really just talk about the technology in just general terms, so that trying to paint a really good picture of what's actually happening. So since I don't have access to anyone to be like, hey Bob, do you want to be on my podcast? We can talk about, I don't know, VPNs. I figured I would just have a normal discussion about a particular topic. And for those of you that have been following for the last couple of weeks or so, I know that I've been doing the data center track for a few weeks now, and it's been going great. But I was talking to a friend of mine, and he was just like, the data center, he's like, it's okay. He's like, but unless you work in that space already, it's going to be, he's like, for you it probably wouldn't be as difficult, but he's like, if you're really not a data center guy, then he's like, I think you'd be probably better off doing security. And I've always wanted to dive deeper into the security platforms. I spent quite a bit of time working on my NPN security and stuff like that, and so I was like, you know what? I'm in no real hurry to go get a certification, really. I've got the better part of 3 years to basically get another Cisco certification. So I've been kind of bebopping back and forth between security and other topic areas that are just interested to me. And one of the things that he told me about is hey, did you know Palo Alto until the end of August has, at least at the time of this recording, has a deal where you get half off of your exam when you register. I was like, no, I did not know that. So I went and I checked it out. So I've got a Palo Alto exam scheduled. I'm still learning Palo Alto, and it's been cool, but I'm more or less just learning to learn, right? I've got I don't have a boss or a partner requirement, if you will, saying Rob Riker needs to be certified on this particular certification or have passed this exam by July 31st. I don't have any of that. So rather than put myself under any undue pressure, why don't we just study whatever, right? I mean, because that's the beauty of having all of your certs up to date, and then you can just go upgrade whatever it is you need to. So what I decided to do is I started kicking off this Let's Talk About Networking series. I want to just, from a high level, just talk about networking in general, because I feel like it's really necessary to take a look at it from the perspective of not necessarily hyper-focused on a particular technology or get it configured, but more or less the operations of the network. What happens with a packet from point A to point B? Let's do an actual packet walk and just describe the operations of what's happening. Because one of the things that I find, especially for the entry-level folks, is, especially if you're studying a Network Plus or a CCNA, there's this the company that I work for, we often do these weekly calls where someone in the industry will get on the call and we'll talk about a particular topic. And we'll go into some level of depth. We'll answer questions that people might have, try to give a little bit of career advice, that type of stuff. So I wanted to take that type of idea, but not necessarily interview anybody. But I mean, if you would like to be on a podcast, I would we'll figure something out. But you know, it's I'm going to talk just in general about networking, like, you know, try to help everyone tie everything together and make it more of like an informational series, not necessarily like, you know, geared to a certification or anything like that. So I know it's taking me 5 minutes to get to my point, but you know, I'm hoping that people will be interested in, you know, diving into the details and stuff like that. So I'm not only going to be focusing on this topology. What I will be doing is some high-level whiteboarding, because I feel like it's necessary to understand from point A to point B what's happening, and or more like from point A to point Z, along all the individual devices that you would flow through, what's actually happening. So guess what? That's what we're going to do. So if I needed to do a deep dive on a whiteboard or anything like that, I will take the time to do that. But for right now, I'm just going to pretty much just explain operationally what's happening. Forgive me as I clear space on my desk to give myself access to my pen pad so that it's easier to work with. So yeah, that's basically what we're going to do. And for the most part, it's just going to be like, okay, you know, what's the deal? Now I'm going to be focusing on like the router here, and there's normal layer 2 and layer 3 communication. So that's where I'm going to start. And let's assume for just a moment that our communication is going to be between this device here and this device here. So what's going to end up happening? What do you need to know, or what needs to occur? Or even better yet, let's talk about a fictitious device that's sitting out here on the internet, right? We'll just call this a server sitting out here on the internet that you want to connect to for whatever reason. Maybe it's google.com or Facebook or whatever the case might be. What's actually happening? So, what's going on? So, one of the first things that's going to end up happening is we need to understand, how does this guy right here get an IP address, right? What does that process look like? Well, in most cases, you're going to be relying on a technique known as DHCP, Dynamic Host Configuration Protocol, which is a way for a device to get an IP address dynamically when it comes onto the network. So if you've got Wi-Fi or you've got a home network that doesn't have a statically assigned IP address, but it's able to get on the internet, it's getting DHCP. There's really no other way of doing it other than statically assigning an IP. So the DHCP process is actually broken up into 4 different little subsets. We have the discover process, we have the offer, we have the request, and then we have the acknowledgement. Now, the discover is going to be a broadcast message. So if you were to take a IP packet and decode it in, say, like Wireshark, in the destination IP address portion of the header, you would see all 255s. That's a horrible 5, by the way. I'm not going to draw that many 255s because that would just be a waste. So we have 255s going out, and it's going to be sent outbound, and this is the destination. 255 is the destination, which basically, when it's received by this guy right here, and he's like, oh, this is a broadcast packet, right? So what he's going to do is he's going to send that information out this way, he's going to send that information out this way, and he's going to send the information out that way. Why does he do that? Well, because a broadcast packet comes in on the layer 2 switch or a layer 3 switch, and what's going to happen is when it comes in on the switch, the switch is going to be like, well, I don't know where to forward this, because both the layer 3 header is 255s and the layer 2 header is all Fs, right? Because a layer 2 MAC address, a broadcast MAC address, is all Fs in the destination header, or destination portion of the layer 2 header, and in the layer 3 header, in the destination portion, it's all 255s. Both mean broadcast. So when the switch receives that, he's going to forward that message out all the ports that are inside of that same network, except for the port that it was received in on. The split horizon rule. Don't send it back out where it was received in on, because they don't know where to go either. So therein lies the split horizon. So let's assume that this guy right here is our DHCP server, right? Well, router 6 is going to get that, and he's going to decode it and go, oh, okay, that's a DHCP packet. It's a DHCP discover. he gets it, and then he's going to be like, oh, well, I happen to have a DHCP pool configured for you. So what's going to end up happening is he's going to respond, and what's going to happen is this first communication is broadcast. O, R, and A, the offer, request, and acknowledgement, are all unicast between the server and the endpoint that's trying to get the IP. He's going to respond with a message inbound back to the source device saying, here's an IP address. Here's the subnet mask, here's a default gateway, here's any DNS information, so on and so forth. The PC is going to receive that and go, oh, well, thanks. That was awfully kind of you. Let's go ahead. I want to say, yeah, I want that IP, right? So that's going to be the request. It's going to go back out from the endpoint back to the DHCP server so that the DHCP server knows, oh, okay, well, he's actually going to take that IP address and go with it. So I'm going to go ahead and put that IP in a binding table. So it'll be an IP to MAC binding, right? And then he's going to send that message back to the endpoint saying, okay, yep, it's yours, here's your release time frame, and you're good to go, right? That release time frame will be like a day or a week or something like that, and you'll be in good shape. You know, everybody's happy. Well, that's DHCP in a nutshell, right? That's basically what's going to end up happening, and from there, now we can actually communicate out of the network. Before that, we might have had an IP, but for the sake of argument, there was no IP, right? The device didn't have an IP address. It came online and needed to figure out where to go. Now, what's actually cool about this is because of the fact that now this guy has an IP address, and let's just say it's 10.1.1.10/24, and we have 10.1.1.1 over here on the router. That's the default gateway is router 6, hypothetically speaking. Well, that's great now because now the switch now knows that 1.1 is on port gig 0/0 and 1.10 is on gig 0/2. He knows that because you get the communication going back and forth, the PC and the DHCP server, in order to pass the information on that was necessary. By doing that, he automatically builds the ARP table. The ARP table is also known as the Address Resolution Protocol. I thought somebody was calling me, pardon me. ARP is basically I know my IP address, but I don't know my the layer 2 header that I need to go send this traffic towards. So ARP is a broadcast communication as well, but it's at layer 2. So if we know the IP address of the source and we know the destination IP address, but we don't know what MAC address this guy has on this particular interface, right? So let's say for the sake of argument that the MAC address here is C, and over here this MAC address here is B. Well, with the DHCP process going back and forth between the PC and the router, and the switch is the middleman, all the traffic is passing silently through the switch. The switch goes, oh, okay, well, I know MAC address C is located on gig 0/0, and I know MAC address B is located on gig 0/2. So the ARP table is built that way. Now, ARP is built on any layer 3 devices, right? So assuming that this guy doesn't have any layer 3 interfaces, then you're in good shape. Up here, there's going to be an ARP table. On the switch, you're going to build what they call a CAM table or a MAC address table. They mean the same thing. Content addressable memory, MAC address table. You know, we have you say potato, I say potato, you say tomato, I say tomato, whatever. You know, you understand where I'm going with this. Regardless of which term you use to reference the dynamic MAC address learning of a switch, there's RAM on the switch that's used to learn the MAC address. And for every VLAN that you create, a MAC address table is automatically generated, as is a spanning tree instance. So basically, if you were to look at it this way, you have a VLAN that you create on the switch will automatically equal a MAC address table, which will automatically equal a spanning tree protocol instance. You know, they're all one for one, right? And this also equals a subnet. That's horrible writing. Let me clear that up real quick. A subnet. You might say, okay, but how is a MAC address table tied to a subnet? Well, the MAC address itself is not tied to the subnet. But in order for the subnet to be operational, right, and in order for a switch to provide a layer of segmentation or separation between, let's say, the server environment and the backup servers, or the wireless network, or the voice network, or whatever else other type of communication you have on your network, maybe the printer network. Always got to remember those printers. You're going to have a VLAN to keep everything separated. A VLAN, in its basic sense, is like taking a switch, right? Take a switch that's got, let's say, a few ports physically on it. And if I wanted to take a normal switch, you go to a Best Buy or Fry's Electronics or whatever electronics store you would use, and you go buy like a Netgear 8-port gigabit switch, right? You go buy the switch and you plug things in. Well, what's going to happen is, out of the gate, if it's an unmanaged switch, it means that all ports are going to be what they refer to as VLAN 1. VLAN 1 is referred to as the untagged VLAN or the native VLAN, which just means that there's no VLAN information that is exchanged or sent between two switches when there's communication between the switches necessary. We'll talk a little bit about that more in detail when we get down to here, and I'll explain what I mean by that in more detail. But if you needed to provide separation, what you would do is you would logically separate the switch into two different VLANs. You put this one here in VLAN 10 and this one over here in VLAN 20, for example. So then these guys right here can talk, and these guys here can talk, but there's not going to be any communication between these guys. This additional communication between them, actually, that won't work at all. Let me do this. Let me switch my color over to green. This will work. This will work, but this will not. Because you can't go between VLANs out of the gate. In order to route or communicate between VLANs, you need some sort of layer 3 device, like a router or a switch or a firewall that supports the capability. So with all of that established, I can sit there and take this guy right here, and I can carve him up into multiple VLANs if I want to. I don't have to, but it's usually advisable. Now, with that being said, I have the subnet, the VLAN created, right? So for every VLAN that I create a MAC address table. I create a spanning tree protocol instance, and I also give myself another subnet. Makes it very, very easy to scale a local area network or a LAN. Great, all that's been decided, right? So we've built the CAM table, the CAM table's been built, and we have all this communication going back and forth, and we're all happy. You know, this guy can talk to this guy. That's literally as far as we've gotten. All this other stuff that's going on doesn't really make much of a difference. So let me talk about the tagging feature really quickly. So I'm here, this port right here is in VLAN 10, and this port right here is in VLAN 10, and so is this one. Well, let's assume that this is VLAN 20 and this is VLAN 20, and I have other ports that are potentially in other ports as well, or I'm sorry, in other VLANs as well. Well, if I want to be able to communicate between the trunk or between these switches, I need to create what they call a trunk link. The trunk just means that you can send more than one VLAN across that particular link at a time. So by default, you have VLAN 1 out of the gate. On a Cisco switch, that's what you get out of the gate. You could add 2, 6, 12, 100, 2161, so on and so forth. The numerical value of the VLAN is actually irrelevant. You just create a VLAN number, and then you can give it a logical name. Like, for example, this guy could be not used, right? Because nobody is supposed to use VLAN 1 because it's considered a security hazard if you do. Let's say this guy here is servers. Let's say this guy right here is cameras. Let's say this guy right here is HR. This guy here is engineering. This guy here is iSCSI in the data center. You know, whatever you need to allocate that VLAN for, just needs to be noted wherever it is that you're creating that VLAN from. Things like that. So that's how that basically works. Now with that being said, if I need to be able to communicate from here out to here, how would I do that? Well, there's actually this invisible demarcation point between this router on this side and this router on this side. Let's just, for the sake of argument, say this is going to be the inside of the network, and this side will be the outside. Now, in technical terms, we would call this the private side, and this would be called the public side. Now, why is that technically a term? Well, because of the fact that the IP addressing that you use will dictate whether it's private or whether it's public. So if I say 10.1.0.0/16 is being used at this location, let's say that all of this right here is one big location. I mean, that's certainly possible, I suppose, but let's say that that's the case. Well, that means that based off this IP address, I would know it's a private address range. How do I know that? Number one, I just do. RFC 1918, right? We have RFC 1918. RFC 1918 is one of the standards that folks like me in the IT industry, specifically networking, are going to reference when we refer to addressing that's private, meaning it's not routable on the internet. So that's going to be your 10/8 range, your 172.16/12, and your 192.168/16, right? So it gives you a lot of flexibility and a lot of scale for what it is that we're talking about. So it gives you a lot of address ranges. When you send the traffic, let's say this is 10.1.1.10, and this is 10.1.1.1. If my default gateway, DG, is .1, that means that I need to send traffic this way, and then the switch will forward it up this direction. Well, unfortunately, the internet routers, those pesky little buggers, they don't take IP address packets that have a source IP address of 10.1.1.10 and allow them to get forwarded out to the internet. As a matter of fact, since this is our internet router, or simulated internet router, obviously, if I was to send traffic out this way, it's going to have a source IP of 10.1.1.10. And then I'm going to have some sort of routing set up to where that's going to get forwarded out here, because the destination is going to be, let's say, is Google 8.8.8.8. Well, here's the problem with this logic. If I send traffic out Windows 10-1 towards the internet, and I send that traffic out, it hits the router says, okay, well, there's a default route, let's go ahead and send it to the CSR internet, and then CSR internet will send it out to wherever he's got to go. Great, let's knock it out. The problem with that is that when you do that, the source IP address never changes, right? So because it never changes, the internet router receives it in on this interface and goes, dropped. Why does it drop it? Because internet routers don't forward RFC 1918 address space. They will drop it. So how do you combat that? Great question, I'm glad you asked. You use a term known as network address translation, or technology feature, whatever you want to call it. NAT, as it's commonly referred to, is how that is accomplished. So what you do in NAT is you need to define a couple of interfaces that will basically participate in the NAT design. So you need an interface that's been specified as inside, you need an interface that's defined as outside, and then you need to create a global statement that says, hey, if I receive packets coming inbound on this interface from a particular source, I want to allow those same packets to be sent out this interface, but instead of keeping the source IP address the same, 10.1.1.0 0/24 as the source, going to any destination on the internet, instead of keeping it this way, I want to translate it from 10.1.1.10 over to, let's say this public IP address out here is 21.6.8.3. So you would translate it from this IP to this IP. And you would send the traffic out then. Now the internet router is going to go, oh, well, I understand 21.6.8.3. That's a public IP because it doesn't fall underneath RFC 1918. This address range does not fall underneath that RFC 1918 address space. So therefore, I know it's a public IP. So that means that the internet routers should know how to get to wherever I'm trying to go. Well, remember, this is the source. I'm translating the source IP into something that the internet router doesn't know how to reach, and changing the source to something that the internet routers do know how to reach. Because at the end of the day, you need to have your device or your packets look like they're coming from something that's reachable on the internet. That is why we refer to this particular feature known as PAT. What's PAT? PAT stands for port address translation. So port address translation. What does that mean? Well, what it's going to do is it's going to take any of these source and destination ports. So it's going to normally look at the source port and go, okay, let's say we're trying to go to wherever it is we're trying to go. Let's say we're trying to go to Google out here. Let's say this is 8.8.8.8 is reachable out here. Well, what you're going to do is you're going to take this IP address 10.1.1.10 and you're going to translate it over to be 21.6.8.3. But my destination port is, let's say, 443. And my source port is, let's say, 1127. Right? Well, what I'm going to do is I'm going to take this port number and I'm going to take it and I'm going to put it over here on the public IP side. So this port right here will actually be now 21.6.8.3, and it's going to be :1127, going to a destination of 8.8.8.8 :443. So NAT is going to actually translate the source IP from 10.1.1.10 to 21.6.8.3. It's going to move the source port from what 10.1.1.10 had to 21.6.8.3 and forward that on its merry way. Then Quad 8 will receive it and go, oh, you're trying to go to Google. Great job. And then it'll go ahead and flip it around and know to send the traffic back to 21.6.8.3. So return traffic. What happens with the return traffic? Well, as long as there's an entry in the NAT translations table, the show IP NAT translations on a Cisco router, it's going to go ahead and it's going to receive that packet back in, look in its NAT table and go, oh, yeah, I do have an entry in my NAT table to allow that traffic to come back in. As long as it does, it's going to go ahead and get translated back to 10.1.1.1.10 and down to Windows 10. And that's NAT. There's really not much more to it than that. Hey, I rhymed. I'm a poet and didn't even know it. Here all week, folks. Please be sure to like, share, and subscribe before you walk away from this video. So that's the basics, right? That's basic, just basic networking and how it operates. Now, that is and literally all I've talked about so far is going from here to here, and then from here to here. Technically speaking, it's this and then to here. Because from here to here is one layer 3 segment, and from here to here is another layer 3 segment, and from here to here is another layer 3 segment. All is great, right? How does it layer 3 segments? Because this is 10.1.1.0/24. This is 21.6.8.0/24, and this would be 8.8.8.0/24. So anytime you have a routed boundary on a particular interface that you have to route to another subnet in order to get to wherever you've got to go, that's another layer 3 segment. So you route it from one segment to another, to another, to another, in order to finally get to your final destination. And that, ladies and gentlemen, is basically how networking works. Now, if you have any questions for me, please be so kind as to put them in the comment section below. If you haven't already done so, like I mentioned, please like, share, and subscribe. And until next time, guys, take her easy.